these beams which are statically determinate, and in this case we will have cantilever and simply supported beams. So these two types of beams will be discussed, and you will see how we can calculate slope and deflection for these beams. Elastic curve is the shape of the beam after it has deflected, because when we apply the load on a beam, the shape will change because of the bending moment. You are already familiar with bending moment, whether it is positive or negative bending moment. Positive bending moment is sagging. When there is positive bending moment, the beam will bend like this, which is concave upward. And when there is negative bending moment, which we call as hogging bending moment, this will be the curve that is concave downward. And if you look at these cases here, this is a part where you will find negative bending moment. And in the case of negative bending moment, the beam is deflecting in such a way that it gives you a curve which resembles this hogging or concave downwards. In this part, where you see the bending moment is positive from this point to this point, and you find that the curve is like this, which is sagging, or we can say it is concave downward. This is a point which is known as point of inflection or point of contraflexion, where you see that the nature of bending moment is changing from positive to negative or negative to positive. So this changes the nature of the curve from here, and you can see that from this point onward, because the bending moment is negative, so this comes in this way as hogging, or we call it as concave downward. Now we move on to see how we can start the calculation of slope and deflection for our beams. As you might be aware, with these cases of bending stress equation, which is given by Euler-Bernoulli, that equation gives you a relationship that m upon I is equal to sigma upon y is equal to E upon R. So we take that equation, and based on that equation, that we can say that 1 upon R, which is radius of gyration, will be equal to m upon EI, where m is moment of inertia of the beam, E modulus of elasticity, I the beam's moment of inertia about the neutral axis, and EI is flexural rigidity. So you are familiar with this equation, so we will go ahead with this, and the flexural rigidity will be constant along the length of the beam if it is not changing in moment of inertia, and the slope and displacement relation of the beam can be written in this way. So if we look here, this is EI d2y by dx2 is equal to m. EI d3y by dx3 is equal to shear force, and DI d4y by dx4 is equal to the rate of loading. So we will start with this equation, which is differential equation of elastic curve, which relates curvature with the bending moment. So this is just a simple solution of the differential equations by applying the boundary conditions, and you will see how we can calculate the values of slope and deflection. You can see here, we should know what are those boundary conditions at every support, because support is not allowing the beam to move from that point. That means it is providing obstacle for movement and also for rotation in some cases. In the case of a simple support or a roller support, the deflection will be 0, but rotation will not be equal to 0. It is free to rotate. So there will be some rotation, so there will be some slope, but the deflection will be 0, and the bending moment also is 0 at the roller support. Similarly, in the case of pin, you have the same situation. The beam can rotate, so that's why the slope is possible, but the deflection is not possible at that point, and also bending moment is 0 at the pin support. So here you can see at the fixed support, what happens in the case of fixed support? Both slope and deflection will be 0. The beam is not allowed to rotate or translate about that point when it is fixed. And this is internal pin or hinge. In that case, M is equal to. Now we go ahead and see how these boundary conditions can be applied to find slope and deflection of the beam by using integration. We will solve this example, which is taken from R.C. Hibbeler Structural Mechanics book, and you will see here this is a cantilever. In the case of cantilever, one end is fixed and the other end is free. Here we have a point load which is applied at the free end of the cantilever. So we need bending moment equation. So take a section here at a distance x and find the value of bending moment. If you see here at this section, we have just a section here, and P into X will be the value of bending moment. It will be hogging, that's why we are taking here minus sign. So this is moment function, and it is better to draw the possible elastic curve for this cantilever. Now, if you look at this, we can write our differential equation in this way. EI d2y by dx2 is equal to minus P into X. And when we integrate this equation, we will get EI dy by dx equal to minus P is constant, then X, when you integrate X, it will give you X square upon 2. This is simple knowledge for you from the course which you have taken in calculus. So this, and when we integrate, we get a constant of integration. So this constant of integration is unknown. We will be finding the value of this constant by applying boundary conditions. So here dy by dx is what? This is slope of the beam at a point x, at a section x, which is taken at a distance x from the free end. So free end is taken as the origin of the axis. When we again integrate this equation, we get EI, and dy by dx will be y on integration, and this will be again a integral of this form. P is constant, x square by 2. When we integrate, it will give you x cubed by 6 plus c1 into x, the constant integrated, so x power 1 plus c2. So this is the equation for deflection, and this is equation for slope. Now these two unknowns are there which we have to find. The boundary conditions are depending upon the values of these slope and deflection at some known points. As we discussed earlier, at the fixed support, both slope and deflection will be 0. It will not allow the beam to rotate or displace about this point B. So we can say that slope is equal to 0 at x is equal to 0, and deflection is also equal to 0. Slope is equal to 0 at x is equal to L, and deflection is also equal to 0 at x is equal to L. We substitute here these values. 0 for slope, PL square in place of x, we put here L. So PL square by 2 plus C1. And the second one, we substitute here the values of deflection and the distance x. So at x is equal to L, again the deflection is 0, so we substitute 0 and PL cubed by 6 plus C1 into L plus C2. Now these two equations can be solved to find the values of C1 and C2. So from here you can easily say that the value of C1 is PL square by 2, just from this relationship. So once you get the value of C1, you can substitute C1 here, right? So PL square by 2, we will substitute, and then we will be able to find the value of C2. So you can say that easily you can find the values of C1 and C2 after applying the conditions at the ends of the beam, and these conditions are regarding slope and deflection. Now finally your equation, which is in this form, we can say here EI dy by dx is equal to minus px square by 2 plus C1. Now C1 is PL square by 2. So we can say that EI dy by dx, so dy by dx is just written as theta, which is slope. So theta is, and then we can write this EI on this side, and this can be written as P upon 2 EI, and within bracket you will have these values of L square minus x square on simplification. So this can be written after substituting the values of C1. Similarly, the value of y, which is your displacement, we can write here in this form. Substitute here the values of C1 and C2 and get this relationship. So this is a simple way for finding the equations for slope and deflection. Now with the help of these equations, you can find slope and deflection at any point of this cantilever beam. Just substitute the value of x and you will get the slope and deflection by using these equations. I hope this is clear. Now we can go to another example, so it will be more clear for you how to find these values of slope and deflection. So this way, if you have to find maximum slope and deflection, you can see here maximum will be at the free end, which is clear from your elastic curve. At x is equal to 0, the value of slope will be maximum and also deflection will be maximum at this point. So we substitute here x is equal to 0. This term will become 0, this term will be 0, this term will be 0, and you will get the maximum values of slope and deflection, which can be written like this. So slope at A, PL square over 2EI, and deflection at A minus PL cube over 3I. This minus sign indicates that the deflection is downward. This is in the negative y direction. Now we go to the next example and see how can we solve this problem. You can see here, this is a cantilever, again with uniformly distributed load with intensity of W per meter. It can be W kilonewton, W Newton, whatever be the value. So we take here the origin of the axis and write the equation of bending moment at section x at a distance x from the origin, which is taken at the free end of the cantilever. Shear force, you can say it will be W here, and then we find this value. This value can be calculated here. Bending moment at section XX minus W into X is the load here, and this distance is x by 2 from the centroid of this load. So force multiplied by the distance will give you the bending moment. So force is W into X, and the distance from its centroid is L by 2. So we can simply write this equation as minus Wx into x by 2, which is minus Wx square by 2. So this is your equation. This is with minus sign here, minus Wx square by 2, and this is minus W into x. So shear force at that section you have calculated, this is minus W into x. Again, starting with the same, M upon EI is equal to d2y by dx2, or you can say that d2y by dx2 is equal to Wx square over 2EI. We can write here in this form, and we already have the expression for bending moment, Wx square by 2. We will substitute here the value of bending moment in place of M, WL square, Wx square over 2EI. So on integration, you will get the value. When we integrate d2y by dx2, we will get dy by dx. And here W is constant, 2EI is constant. We can take it outside the integral, and we will be integrating only the term x. So this is x square. On integration, x square will give you x cube by 3. So that 3 and this 2 will make it 6. So we get this value as Wx cube over 6 EI, and a constant of integration. Here we can say a constant integration A. You can take any value, A or C1, or any other letter which you like. But this has to be determined in the same way as we have done in the previous problem by applying the boundary conditions for this beam. Because it is cantilever, so boundary conditions will be same for this. At this fixed end, x is equal to L, slope and deflection both will be equal to 0. You can also use these online calculators for slope and deflection calculations, which are available on this website. These are authentic cases for cantilever, and you will get the values, correct values. Again, integration of this equation for slope. So this is your equation for slope. We integrate again to get the value for deflection. So dy by dx on integration gives you y, and this term x cube by 4. So that 4 and this 6 will make it 24. So Wx power 4 over EI plus A into x on integration plus another constant of integration, because we are integrating second time. So this constant will have different value, and your job is to find these constants A and B in the similar way. So we can apply the same conditions, boundary conditions at x is equal to 0, x is equal to L, y is equal to 0. At x is equal to L, dy by dx, that slope is also 0 at the fixed end. So the second boundary condition, when we apply, it gives you this. This is boundary condition for slope. If you come back, you will see here, this is your equation for slope. So when we substitute here, dy by dx is equal to 0, and you will get A equal to this. We substitute x equal to L, and this way you can get the value for A, which is WL cube over 6 EI. So this will be the value which you can calculate easily at x equal to L. So here we have this value, L cube, whereas the first boundary condition yields these values, and we can see here the value of B is calculated from the second equation. We substitute here in this equation at x is equal to L, your deflection is 0, and we already have the value for A, so we can calculate the value for this second constant B, which gives you a value here like this. So B will be calculated in this way. We substitute here these numbers, and that gives you the value for B. So B comes out to be minus WL4 over 8EI. We substitute these values for A and B in our equation. The original equations was like this. This is for slope, so we have got the value for A. We will substitute here. This is the equation for deflection. We substitute here the values for A and B, which we have just now determined. So we write here these values. This will be your equation for displacement. So we can calculate maximum deflection and maximum slope from that equations. If you see here, we will substitute those values and get at the point of maximum slope and deflection. You can see that it will be like this. This will be the deflected shape or the elastic curve of this cantilever. So you will have maximum deflection at this point. This will be maximum value, and the slope will be, you can say, if I take this one, this will be the slope. The line, this is straight line, the slope of this tangent at this point will represent the slope at this point, which will be maximum slope and maximum deflection. So our aim is to find the equations for slope and deflection. Then in that equation, substitute the conditions for X for maximum slope and deflection. This way you can easily find the values for slope and deflection. So this is your integration method for cantilever. Now we will solve for simply supported beam. In the case of simply supported beam, we will take this case of uniformly distributed load on the beam. So there are two supports and the load is uniformly applied over the entire span. Because of the symmetry of this loading, the two reactions will be equal, and in this case we can say that the reactions will be equal to, because W into L is the total load, it is W per meter, and the length of your beam is L, so W into L is the load. If we take here, the reaction will be half, so WL by 2 will be the reactions. Otherwise, you already know how to calculate the reactions by using equations of equilibrium. Sigma Fy equal to 0 and sigma m equal to 0. We can calculate the reactions. If you want, you can join another class for shear force and bending moment, where we explain how to find the reactions for simply supported beam when there are different types of load. But here it is a simple case. There is only uniformly distributed load for the entire span. So because of symmetric loading, the two reactions will be equal. Here we have these two reactions, and then you can see here this equation for bending moment at a section X we have to write. This is X here. So at section X we have this value WL by 2 into X. Now there are two forces. You have to be very careful when you are writing the equation now. This force is acting upward. So because of this force, it will be giving you a curve which is like this. Taking your beam in the upward direction. Like this. Because of this force. The force is upward, so it will try to lift this end, and the shape will be, probable shape will be like this. When we look at the second load, this is UDL, uniformly distributed load. This uniformly distributed load is acting downward. So because of this uniformly distributed load, the diagram will be, the curve will be like this. The bending moment will be hogging. It will try to bend the beam in this way. So we are going to, the net effect will be, net bend elastic curve will be like this. This will be your elastic curve for the beam. Now we have these two bending moments. So here we write the equation with plus and minus sign for hogging. And always remember that all downward loads will be giving you hogging bending moment. So we will use minus sign for those. And all upward forces will give you sagging bending moment. So we can substitute here the values WL by 2 into X, the bending moment due to this reaction, and then bending moment due to this uniform load, W into X, because the length is X meter. We are considering only this much portion on the left hand side. So this is W into X, and then as we have done in the previous case for cantilever, we take distance here at a center of this portion. This distance is X, so this will be X by 2. So at a distance X by 2, we can say this will be the centroid of this loading, and we can easily calculate this value for bending moment here. So WL by 2 into X minus WX square by 2, these are two components of this equation for bending moment, and we write here. Now differential equation for the elastic curve, d2y by dx2 is equal to m upon ei. Substitute the value for m here. So 1 upon ei into m. In the bracket we have WLX by 2 minus WX square by 2, and then on integration on this we get on this side dy by dx, then integral of these terms here, WLX by 2 minus WX square by 2. So this is WL X will become X square by 2. So this 2 and 2 will make it 4. WLX square by 4 ei minus WX square. So again, you see when there is power 2, it will become cube, WX cube over 3. So 3 into 2 will make it 6 in the denominator, plus this constant of integration. So WLX square over 4 ei minus WX cube over 6 ei plus a. So this is constant. We can calculate in the similar way as we have done, but the boundary conditions will be different because there is no fixed support here. Both supports are simple supports here. Now integrating once more, we get here y. When we integrate dy by dx, we will get y equal to WLX cube. So cube, and then in the denominator 3, so 3 into 4 will make it 12. So WLX cube over 12 ei minus wx4 over 4, that 4 and this 6 will make it 24, plus ax, integration of constant will give you ax plus b. So these are two constants of integration for this simply supported beam. Now we go to the next slide and see how can we find these values for A and B by applying boundary conditions. In this case, you can easily see that at these 2 points the deflection will be 0, but we don't know at which point slope will be 0. There is no fixed. We can say that because of the symmetry, the slope will be 0 because maximum deflection will be at the center, but we will not use that condition. These are two definite conditions, that deflection is 0 at x is equal to 0 and deflection is 0 at x is equal to L. So these are the two boundary conditions which you will be using, and you can see here like this. This is a boundary condition at x is equal to 0, y is equal to 0, and second at x is equal to L, y is equal to 0. So in these two cases, we will substitute the values. So when we apply these conditions, if you see here, x is equal to 0, y is equal to 0. Come back here. When I substitute here, x is equal to 0, 0, this term will be 0, and y is equal to 0, this will also be 0. So that's why we can say that this b plus 0, 0, 0, that will give you the value of b equal to 0. So b is 0. Now we apply the second condition, and the second condition is that x is equal to L, again y is equal to 0. We substitute these values, and after substituting these values we get this. So here is your equation. We can look again at this one. So y is 0, we substitute here x equal to L, here also x equal to L, but b is already 0, so there will be no need for b, and we get this form. 0 here, WL4 over 12 EI minus WL4 over 24 EI plus A into L. So this gives you the value of this constant of integration A, and we can substitute these values of A and B in our equation for slope and deflection. If you see here, you can substitute here, and this will give you the equation for slope. The value of A will be substituted here. So theta equal to, this is your slope here, theta, and this is deflection. So from this equation we can get the slope at any point of this beam. Now you can realize that the maximum slope will be at the ends. When the beam will bend, it will give you maximum slope at the ends, and there will be a point at which there will be 0 slope, because the nature of slope will be different. Here the beam is rotating in this way, in the clockwise direction, and in this case the beam is rotating in anti-clockwise direction. So there will be a point in between. Because of this symmetric loading, that point will be in the center of the beam here. So that distance will be L by 2, and we can also calculate the values of maximum deflection. That maximum deflection will be always at the point of 0 slope. So that is the case for finding the value for maximum deflection. You can always say that the point at which slope is 0, you will have maximum value of the curve. So here we have this equation is for slope, and this is the equation for deflection, and this is equation of the elastic curve. Derivative of this equation means the slope comes here. If we substitute here theta equal to 0, you will be able to find the point at which slope will be 0, and that will give you the value x equal to L by 2. When you substitute here this value equal to 0, you will get x is equal to L by 2 for maximum deflection. So always remember that at the point of 0 slope, that deflection will be maximum. So we have got this relationship, and this is coming from your knowledge of calculus. You must have studied maxima and minima of a function. For maximum value or minimum value, dy by dx should be equal to 0. The slope of that function at that point should be equal to 0. So we substitute here and then we can calculate the value. Okay, now we'll go to this situation here. So this is the value of y. This is your equation, and in this equation, if I substitute x equal to L by 2, I can easily get the value for maximum deflection. So this way we can reach at the point, and if you want to find the slope at A and B, you can calculate the value from the equation of slope. Maximum slope will be at the supports here. So in this equation, if I substitute x is equal to 0, I will get slope at A, and if I substitute x is equal to L, I will get slope at B. So theta A and theta B can be calculated here at these 2 points. So this will be the value for theta A, and this will be the value for theta B. You will get these values, and you can say it will be with plus and minus, so different signs according to our sign convention. You can see these values. Now we have reached at this point to get maximum deflection. If you look at this, we can solve one problem because we still have some time. So in this case, we will try to do one question here. If we have this cantilever, with a load of 10 kilonewton. In the similar way, we can write the equation EI d2y by dx2 EI d2y by dx2 is equal to, so we take bending moment at distance x here, So this value will be minus 10 into x. And then we can integrate this equation. So we can say that will be d2y by dx2 is equal to minus 10x upon ei, this whole thing. So this will be dy by dx after integration. We will have here 1 upon ei and in this bracket you will have minus 10 x square upon 2. Okay. Yes. Plus a constant of integration. When we again integrate, you can say easily we will get y equal to 1 upon ei and here minus 10. This x square will become x cube, so 3 into 2 6 minus 10 x cube over 3 into 2 6 plus ax plus b, another constant. So we get this as equation for deflection. Now to find the values for a and b, we apply the same conditions. At x is equal to L, slope is equal to 0, and at x is equal to L, deflection is also equal to 0. You can see here. So when we substitute these conditions, we can see here at x is equal to L, you have theta equal to 0, when we substitute this condition here, we will get here this value 0, and here you will substitute x equal to L. So we can say that from here this is 0, 0 equal to minus 5, and this L is 2 meters suppose. So we substitute this value. So L is equal to 2. So here 1 upon ei and this is minus 5 into L square. L is 2, so it is 2 into 2, 4. Plus A. So from here you can say that A will be equal to 20. This EI multiplied here will be 0. So A is equal to 20. Now we can find the value for B. So once we find the value for B, we should not forget to substitute here A equal to 20, and now you will see we can find the value for by substituting that second condition, which is at x is equal to 2, you have y equal to 0. Now we substitute here y equal to 0. On this side it is 0, and then we have 1 upon EI and minus 10. Now in place of x we will substitute 2, so 2 cube will be 8 minus 10 into 8 divided by 6 plus ax. Now a is 20, so 20x, and x is 2 meter, so 20 into 2 plus b. So b is unknown now, and we can easily calculate the value of b from here. So b can be calculated. B is equal to this number, and we find this value for b, which can be easily calculated as, so this is 40 by 3. B is equal to 40 by 3 minus 40. 40 by 3 minus 40, which gives you, on simplification, the value will be minus 80 by 3.